All right, woo, 12 o'clock, straight up. Time to rock and roll here. All right, so your homework is going to be due a week from today, and hopefully we'll get far enough into these slides today that I can review it, and it'll all make sense to you. Anyway, that's my plan, and I'm sticking with it. So this is where we wound up last time, so we've already talked on this slide, so just for continuity. So we're talking about tuning boilers, adjusting the amount of combustion air to just the amount that we need for efficiency considerations. So factors that we have to consider when we think about oxygen limits on boilers. The fuel type, different sorts of fuels are going to require more or less air for appropriate combustion. The monitoring and control method that we're utilizing on the boiler. We'll talk about that a little bit. More sophisticated control system will allow us to do a better job. The oxygen sensing location. Where are we taking these measurements? Where is the probe that is accessing the flue gas? Burner condition, certainly. We could have maintenance issues on a burner. And until you fix that, you're probably not going to be able to get very good control of your excess air. And boiler load affects the required oxygen level. Okay, so this is cut and pasted out of that steam system survey guide that I sent you. And by the way, I think we were supposed to have read the first 3 chapters and sections 4.1 and 4.2. I want to go ahead and expand that assignment to read the rest of chapter 4. Chapter 4 is a pretty long and in-depth chapter, and so you need to start reading your way through that. It should go right along with the lecture, and maybe we'll fill in some gaps and some things that don't get mentioned in class. But this is cut and pasted from that document. And so what this table is trying to tell us is, based on fuel type and based on how sophisticated our control system is, what can we expect? What's about the lowest either excess air or O2 content, and what would be the maximum that that you should ever consider having? And of course, so long as we're burning the fuel, less air is better, but we can only cut it back so far. And we'll have some diagrams here and define these, but basically an automatic flue gas control system has a flue gas O2 sensor and continuously measures that O2 level, which is the same thing as measuring the excess air, and can make adjustments instantaneously to changes as boiler load changes, as ambient weather conditions change, etc. A positioning type control system simply positions the air damper or the air control off of the position of the fuel valve. So basically what happens is the steam pressure is measured, and if steam pressure is high, then the fuel valve is closed some, and then the air, there's like a jack shaft, a mechanical linkage that reduces the capacity of the fan. Okay, and that's not nearly as good as sensing your air or oxygen levels directly and controlling the fan off a measurement. It's just a mechanical linkage to the fuel valve. So you can see if you look at the natural gas column there, if we have an automatic control system, we could expect our flue gas oxygen O2 measured content, and that's on a volume basis, between 1.5% and 3%, which would be very, very good, which would be excellent control. If we have a positioning control system, it's just not going to be as good, and we would expect a minimum of 3 to perhaps as high as 7%. And so on the right-hand side, we translate those oxygen measurements into excess air estimates. So for natural gas as a fuel, 1.5% O2 in the flue gas equates to 8.5% excess air. So whatever stoichiometric air would be, you would be introducing an additional 8.5%. And that's considered very, very good, okay? At the 3%, that equates to 18% excess air. And likewise, at the 7%, the maximum on the positioning O2 control, that's 55%. So however much you need, if you need 10,000 CFM, you're providing over an extra 5,000 CFM that's just coming in. You know, a little bit of that you need, but a lot of it's just coming in cold, going up hot, taking energy away from your boiler. So you can see. And so we've got diesel fuel, we've got heavy fuel oil number 6, we've got pulverized coal, and we got stoker coal, which is chunk coal. You know, 1 to 2.5 inch diameter chunks where it's just been, you know, kind of crushed up a little bit, goes in on a conveyor and gets burned in the boiler. And so you can see, depending on the fuel, you know, stoker coal, the best number on the page is 3.5%. So you're not going to get as low based on stoker coal compared to, say, natural gas or fuel oil. Okay, so here's a diagram showing what a positioning control system would look like. And so at the top of the figure, we see a pressure sensor transmitter, which is sending a signal to the steam pressure controller, okay? So, you know, the boiler has a set point in terms of pressure. Maybe it's 100 pounds like Tech, maybe it's 400 pounds like Frito-Lay, maybe it's 800 pounds, you know, whatever. So if, you know, and you got steam supply going out to all of your steam users. Well, if somebody starts taking more steam, then what's going to happen? The pressure is going to start going down. When the pressure starts going down, that pressure sensor sees it, sends a signal to the controller and says, hey, make some more steam. So what happens? So the controller, that combustion control drive, moves in order to open the fuel valve. That's how you make more steam. You put in more fuel. And you see we've got a jack shaft and a rod that also positions the air control damper. And we're showing like a jack shaft, a cam, which is adjustable at different firing rates so that you can do the best you can to get it tuned up. And then the combustion air goes off to the burner. So that's what we mean by positioning control. Now, we'll probably talk a little more about fans at different parts of the course, but a fan is basically a constant volume device. It sits there and it runs at a given speed, and it's going to want to push the same CFM, cubic feet per minute, of flow rate. Well, in the wintertime, that air getting into that fan is probably colder. Now, if you've got an air preheater and all that, maybe not. But a lot of smaller boilers don't have that. And so they're taking air from the boiler room or sometimes from outside. Well, when it gets colder, guess what? That air is denser. So a cubic foot contains more molecules, okay? But if that fan is blowing the same cubic feet per minute, you put cold air in it, you get more molecules of air into your boiler. Well, that's going to affect your tuning on the boiler, your air-fuel ratio, okay? So if you have a system like this, if you tune it during cold weather, then you're probably going to get a little bit less air because the air is denser. Then all of a sudden it warms up outside. And if you don't retune it, then you're not going to have enough molecules because it's going to be trying to blow the same CFM at a given firing rate. And so you wind up with rich combustion, not enough air. Likewise, if you tune it in the summer when it's hot outside, you get more CFM because there's not as many molecules in a cubic foot of air. And then if you don't retune it, it gets cold outside, then you get way too much oxygen when it gets down to 10, 15, 20 degrees. And so If you're going to run in a climate like ours, if you're going to run a boiler like this, it needs to get tuned at least twice a year, going into the winter months and then coming out of the winter months, going into the summer months when it's warmed up, in order to be able to halfway control this oxygen content or the excess air going in. So these things are cheap. It's what comes on the inexpensive boiler. You buy the cheap control system. This is what you get, and you pay an efficiency penalty for it. Okay, an automatic oxygen trim or an automatic control system. You see now in the boiler exhaust gases, we have an O2 sensor. And an O2 sensor sends a signal to the combustion controller, and basically that signal drives the air control damper or speed control or whatever the mechanism is by which you're controlling the capacity of your fan. So you've got an independent control loop that has set points of its own that's trying to minimize or optimize that O2 reading. And then you've got the pressure sensor transmitter controlling the fuel valve, which is also sends a signal into the combustion controller. So we've picked up an automatic control loop that is trying to optimize the amount of air that fan is putting into the boiler for combustion air. So that's kind of the difference in the two. Another slide here. Some of these are a little bit redundant. This is just another depiction of the positioning control system, and maintains position relationship between the fuel and the airflows. So, and then the automatic, we've got the flue gas oxygen sensor feeding back into it. So those 4 slides basically illustrate the same concepts. Okay, so a stack loss evaluation, these are the measurements that we need to take. We need to know the flue gas exit temperature after the last heat exchange surface. We need to know the combustion zone exit oxygen content. And let's talk a little bit about the location of that measurement. Let's go back to the boiler. So we want this sensor to be as close to where the gases exit the boiler as possible. Because if this sensor is downstream someplace in this ductwork, it's very possible that air could leak into that flue gas, especially if you have an induced draft fan. If you have an ID fan, it's sucking those gases out of the boiler, and so the pressure in the ductwork is below atmospheric. And so if you have a leak in the ductwork, any place where air can leak in, then you're going to have air entering those flue gases after they've come out of the boiler. And so you might have 5% oxygen coming out of the combustion zone, but you might measure 7 or 8% at a downstream oxygen sensor, which would not be indicative of your combustion situation. That's indicative of your combustion situation plus air in leakage into the flue gas. And so you would, if you put that signal back into your control system or tried to tune your burners based thinking that was what was going on in your combustion zone, you would be making a mistake. You would cut back the air too far, and you would wind up with a situation where you could not burn all the fuel effectively. So we have to be careful where that flue gas oxygen sensor is located, and that the reading that it's getting is really indicative of what's going on in the combustion system. Okay, ambient temperature, we need that. We need to know what fuel we're burning, fuel composition, which in most cases is pretty easy. With coals, it's a little more difficult because one load of coal is never identical to the next load of coal. because we're digging this stuff out of the ground. You can say that about natural gas as well, but I think the natural gases are more within a tighter band than sometimes the coals are. Fuel oil should be really a pretty consistent fuel. And flue gas, combustibles concentration, you're measuring your CO, that's a combustible, or unburned hydrocarbons, or unburned fuel molecules that are in the flue gas. So how can we actually do this? Well, there's a couple of ways. It's really turns out to be pretty simple. There are online calculators, and Measure has a stack loss calculator in it, and I'll pull that up here in just a second. And we also have stack loss tables that are published for different fuels. So we'll go through both of those methods. So this is a stack loss table for natural gas. So you see on the left-hand column, we have the flue gas oxygen content, and that's measured on a wet basis. Okay, we've not talked about wet and dry basis. Most portable combustion analyzers are, most of the time, I think, these measurements are taken with water vapor still in the flue gas. But some more sophisticated, high-cost instruments want you to dry that flue gas, want you to condense out that water vapor before you put it in the instrument. And so those instruments would measure on a dry basis. And so you're going to get a different number because, you know, this is a volume measurement. And so, or you can think about it as a particle count. Well, if I take all the water vapor out, I have fewer particles. If I have the same number of oxygens, then I'm going to get a larger percent than if I do on a wet basis where I have more particles present. The dry measurements, what they usually do is they'll run that sample through an ice bath. They'll just put it through a line. It could actually be immersed in ice, or it could be in a refrigerated unit that just cools it down to the point that the water is going to condense out. And then they'll have a little centrifuge or a little way to separate all the water droplets out. And then the gas comes out of that and goes into the combustion analyzer. Okay. So that's how you could take a dry measurement. But these tables, and if you just look at a table, you need to know whether the table is prepared for oxygen measurements on a wet or dry basis. And then in the columns, if you look up at the top, you see, well, we're reading stack loss, and that's the percent of fuel higher heating value input. So this table is based on higher heating value of the fuel. Okay, and then the next line down says net stack temperature. So that, like that row of dark numbers at the top, 155, 180, 205, 230, etc. That's the difference between the flue gas temperature and the ambient temperature. So that subtraction has been done in that column. If you look down at the bottom, you'll see an actual flue gas exhaust temperature and an ambient temperature. And so you see that 225 minus 70 is 155. But it is that net stack temperature is the temperature that you want to enter the table at. And you're not always going to match the two numbers at the bottom, but if you get the net stack temperature correct, then that's what you're concerned with, okay? And so then, you know, you may have to interpolate. You may wind up doing a double interpolation in the table. Well, okay, you know how to do that. So not a lot of fun, but it's not the end of the world either. So that's shows a stack loss. So for example, if I'm running, say I'm running 3% oxygen, and let's say I've got a net temperature of 305, 3%, 305, I'm saying that says 17% of the higher heating value of that fuel is being thrown up the stack in combination of excess air and temperature losses. And so then we have in the slides, we have a table for, the first one was natural gas. This is diesel. Number 2, fuel oil. And the numbers change a little bit. Number 6, that's really thick, very, very viscous type fuel oil. And that's low sulfur, and this is high sulfur. And then we have typical Eastern coal, which would be a bituminous, most likely. And then we have typical Western, which tends to be more anthracite, subbituminous. And then we have greenwood. And greenwood, our moisture content is roughly 50%. I have some tables, they're not in here, for dry wood and other fuels. All right, I mean, you can go back to your combustion principles in your thermal book and calculate all of these things. You can set up a little program and calculate them. That's what people do. It's real handy to have the tables or an
Dr. Cunningham?
Calculator. Yes?
You said that the greenwood has 50% water content. Is it possible at all to reuse that water, or is it just too dirty to use?
Well, it doesn't get reused directly from the wood. If you had a condensing economizer, you could go ahead and put that greenwood in the boiler, and then the water vapor would come out on the exit side, and then you could condense it out of the flue gas. People do that, and sometimes will reuse that water. It usually has to be cleaned up. Well, it depends on the use. You know, I guess if you're mixing it with, you know, I don't know. I'm sure there's uses that don't, but most people, if they're going to reuse that water, will do some cleanup on it before they repurpose it. I mean, there is an industry, the wood drying industry takes this green wood and puts it in kilns in order to dry it. And they basically usually have a steam source. They usually burn wood waste and then make steam. And then there's actually drying programs, and it's most of it's computer controlled. But they'll heat it up to like 180 and cook it for a while, and then they slowly cool it off. And they'll dry that moisture content down to between like 6 and 8%, which is the wood that then they would sell to a furniture manufacturer, or somebody's making pallets, or, you know, somebody that's constructing something out of wood. Those people don't want greenwood. So there's a whole industry. I have a friend here in town, Parker Bowles, owns Hermitage Hardwoods, and he's made a lot of money over the years buying green wood and from the sawmill, and then drying it and then selling it to other manufacturers. So that's a whole industry in and of itself.
Okay, thank you.
Yes, sir. Thank you for the question. Okay, so that's the green wood. Okay, so our summary slide on combustion management. Basically, our management principles are pretty simple. Add enough oxygen, i.e. air, excess air, to react all the fuel, but at the same time minimize the extra air to limit the energy loss. And we want to measure, monitor combustibles and excess air levels to identify problems. Measure oxygen content of the boiler exhaust gas. We can do that. It's best to do it continuously. More sophisticated control systems do that. Some people just do spot checks. Check it, you know, once a month, whatever, once a week. Control oxygen content within minimum maximum range, and that range is set by the sophistication of your controls. And it's always good to challenge what is the standard operating practice. You go in a plant, you stick your combustion analyzer in the stack, and you measure 7.5%. They're burning natural gas. And yeah, guys, this is not real good. Of course, you got to look at the boiler load. If the boiler load is 25, 30%, that may explain part of that, because at lower boiler loads, you have less turbulence, you don't have as good mixing, and you have to make up for that by putting in more combustion air. Now, how much do you need? Well, that's a good question. The way to tell is to put that combustion analyzer in the stack and start periodically reducing the amount of combustion air at a given firing rate. See how low you can take it before you start seeing unburned fuel. You start seeing CO jump up. You start seeing hydrocarbons jump up. Boys, that's the limit, you know? We can tolerate a little bit of that, but not a whole lot. And so that's what sets the real limits on what's possible in a given situation. Repairs, it could be that we have maintenance issues. If we have a positioning control, we might consider upgrading to an automatic control system. And we certainly would consider combustion tuning. Getting a boiler tuned is not a very expensive proposition compared to the amount of fuel that's burned in a year or in 6 months. It might cost you $1,500, $2,000 to get your boiler tuned, but you may be looking at hundreds of thousands of dollars in potential savings. So, I mean, and to purchase a combustion analyzer, I've got several combustion analyzers that we use. Someplace probably between $3,000 and $15,000 will get you a combustion analyzer. Most the $15,000 one's going to measure more stuff and probably be better. But for basic oxygen, you can get an instrument, a handheld portable instrument that'll do it for probably $3,000. Anybody operating a boiler should have that capability. Now, I will say what you get into on those things, the small handheld instruments are fine if you've got a duct or, coming out of your boiler that's this big or this big. If you go to a big boiler, you've got a 6-foot, duct coming right out of the boiler carrying that flue gas. Well, if I got a handheld instrument, I got a wand about that long and I stick it in there. So how, and I get a reading, but how well does that reading indicate what's really going on across that whole duct? That's what you don't know. So to get into testing on larger boilers, you need multiple sampling ports, or they buy sampling ports that you can move across and that are long enough that you can go across the whole duct. And you can measure it here, 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 and average it or get some kind of an idea. Make sure that the reading that you're getting is really indicative of what's going on. Because, you can have all kinds of weird flow profiles coming out of the boiler. And if you're pretty close to that, you're over on the side, and I'm sticking into a duct this far that goes all the way to that wall. Sometimes it's hard to have a lot of confidence in what you're measuring. So built-in instrumentation would have sophisticated sampling apparatus to take that into consideration. But if you walk in with your handheld, now, some things you can do, you can take like a stainless steel tubing, and you can take a longer piece of tubing and stick that into the flow, stick your combustion analyzer into the end of that and tape it off like with duct tape or something to make sure you're not leaking. And then that probe is long enough, you can move it back and forth, and you can kind of do a traverse across that duct. But there's, anytime you're taking measurements, you have to be careful that that you're really getting accurate readings that you can make controlled decisions off of. Okay, so let's do a little example on our boiler here. So determine the stack loss. So we're burning natural gas. Flue gas oxygen content, 7% by volume. CO2, 6%. CO, approximately 0. That's good. Unburned fuel, 0. Flue gas temperature, 450. Intake air temperature, ambient temperature is what we sometimes call that, 70. And the fuel temperature is 70, which we really don't use the fuel temperature in this calculation. So we see the net flue gas temperature is 450 minus 70. So that's the number we're going to take to the table. So there's our stack table. What was that? Yeah, 380. Okay. So I go to the 380 column and I go across at 7%. Well, guys, that's not too hard. You know, just about anybody with a little sense could use a stack loss table. So 21.2%. So 21.2% of the higher heating value of that fuel, the energy content of that fuel based on higher heating value, is going up the stack. A pretty significant loss. Okay, so that means the stack loss is 21.2. The combustion efficiency. Okay, you've got an overall boiler efficiency, which is all of the losses included. The combustion efficiency is just the stack loss. So 100% minus 21.2, 78.8, that is the combustion efficiency. The only loss is the stack loss in combustion efficiency. Okay, and this is the calculator that's in the steam system assessment tool where you can put in this. And, you know, sometimes these things don't agree exactly. This one says for this same combination, 450, 70, and 7%. For natural gas, it says 21.3. So we've got a 1/10 difference. So let's, I've got measure. Let's see if we can play with measure for a minute. Okay, so we've got, these are the big assessment programs, and these are little calculators that help us. So I think we've got a stack loss calculator right here. Okay, so we need to tell it what fuel. So we're going to do gas, typical US natural gas. Stack temperature was what, 450? And this will solve for either excess air or oxygen content. Oh, this is what I want to put in. I'm sorry. I want to put in the oxygen content. And so we said 7. And the ambient temperature, what, we were 70, weren't we? Oh, was it 70? Oh, I said generate example and it canceled me out. 450. There's a way to screw it up. I'll find it. Okay, so this one says 21%. So these numbers are a little bit, there's a little bit of movement from one source to the next, but there you go. It's not hard to determine a combustion efficiency. Now, if I was trying to calculate an overall boiler efficiency to put into the code, then I would estimate a shell loss. You know, we had some stuff earlier on a shell loss, might be a 0.5%, 1%. If I was really doing, you know, the best work I could, I'd take an infrared camera out, I'd shoot the sides of the boiler, I'd calculate the average temperature, I'd get the area, I'd do a natural convection loss to the boiler room, and then figure out what percent that was of the input energy, and you know, that would be my shell loss. So for this program, your boiler efficiency is 100% minus stack loss minus shell loss. The blowdown is you give this thing the information on blowdown, and the blowdown loss is calculated as part of the simulation. So you don't have to give, you don't have to estimate the percent blowdown loss for this program. We'll get back to this in a little while, hopefully. Okay. So our summary on indirect efficiency, it's 100% minus the summation of all of the losses that we have included in the analysis. So it could be 100% minus a stack loss, blowdown loss, shell loss, maybe other losses that we decided to calculate and include. So for this boiler, we did the first three, and if we subtract those off, we get 77.4. If you remember, the direct efficiency evaluation was 77.1. Well, that really does make sense because that direct efficiency has every loss. Remember, that direct efficiency is what? Mass flow rate of steam times enthalpy of steam minus enthalpy of feed water divided by the boiler input energy. And so it's got every loss that the boiler sees, okay? This one just has the losses that you choose to include. And so the fact that the direct efficiency evaluation would turn out to be a little bit lower should give you some degree of confidence that, hey, at least it didn't turn out the other way around, which would give you not so much confidence. You know, but of course, I mean, you're never going to get a perfect answer. You just have to get a good enough answer. And that's dependent upon what your purpose is in doing the analysis. Okay. Let's look at an example here. Boiler loss example, natural gas. This is our example boiler. $10 a million fuel, 400 PSIG, 700 degree F saturated, I'm sorry, superheated, steam leaving, ambient temperature 70. Current combustion efficiency 78.8. We're making 100,000 pounds of steam an hour. Capacity is 120. We got flue gas oxygen at 7%. We got exhaust gas at 450. And it was costing $13 million a year to operate this puppy. Okay, so, well, what would you want to look at? They hire you, a highly paid consultant. You come in, you review all their data, sit down, talk to their boiler operators, get this picture on the board and say, well, boys, we got to save some money here. I got to justify my, $10,000 fee for coming in here for a week, whatever it is. Well, the first thing I'd look at is I don't like 7% on a natural gas boiler. I think we can do better. I think we could at least tune this thing up. And I'm not real crazy about 450 degree stack temperature going up. Now, you start asking questions, well, you guys always run 7%. What's the boiler load? Well, the boiler load is what, 100,000 out of 120, so it's pretty high boiler load. So they can't claim poor mixing. They're way too far up in the load chain for that. It may just be, a cheap or not well tuned boiler or a cheap control system. 450, does it always run that high? Look back in the log sheets. 2 years ago, under the same conditions, was it still 450? Or was it 375, 380? Maybe something's dirty. Maybe you're fouled on the flue gas side or on the water side. Maybe you got some fouling involved. Or maybe this thing, just runs high because they didn't buy a whole lot of heat transfer surface. There's lots of possibilities here. But those are two, stack loss is the largest loss of the boiler. So that's, you want to save big money, you got to go to the big loss. So that's where you're going to go first. So those are the two things. Flue gas exhaust temperature. Okay, so, let's say that we're going to run some numbers here. And this is the kind of stuff that you're going to do in this homework, okay? And you're going to do it in the measure code. Okay, so, well, if I go back to my control parameters, let's say I got positioning control. So I got, I could expect a minimum of 3, a max of 7. I'm running 7. Well, why don't we say if we tune this thing, we could get it to 5 anyway. Maybe we could get 3.5 or 4, but we ought to be able to get to 5 unless there's some extenuating circumstances. Okay? So let's say that, just do an order of magnitude, importance of tuning So we're going to assume that we reduce the oxygen content to 5% from 7. So you see at our initial condition of 7%, 21.2% stack loss, we could drop that to 19.9% if we could just tune this thing a little better, reduce that O2 by 2%. Well, so here's how we can calculate. Here's how we want to calculate this. We want to go 1 minus the existing, the starting efficiency, and this we're doing on combustion efficiency, right? Because that 78.8 is just what? 100 minus 21.2. And then we divide it by the adjusted. So 100 minus 19.9 is 80.1 times that initial operating cost. That will estimate $220,000 a year in savings by tuning the stupid boiler. It's going to cost you a couple $1,000. That'd make you look real good. You show that to your boss. Call up the local boiler, maintenance folks. Hey, you need to come out here and tune this thing. Come out, tune it, give you, $1,500 invoice. You pay it. 6 months later, you have them do it again. At the end of the year, you put $220,000 in your pocket. Pretty good investment. I would probably do that for sure. Okay, well, what else could we do? Well, so we're saying that we started at 7, we got it down to 5. Well, okay, what if I could sell the boss on a new automatic control system? Put in an O2 sensor. Trim this thing. We're gonna buy the state of the art. We're gonna control the holy fire out of this boiler. Let's see what that would, is it a good investment? Can we make money on the deal? Well, let's see. So, the first thing you would assume is that we did tune it. We did tune it. It's just too compelling to not tune it. Too cheap. So then we'll base this on assuming that we have tuned it and we got it down to 5%. But if we're running at 5% now, well, gosh, if I go this automatic control system, I can get it between 1.5 and 3. Okay, so we'll make another assumption and rerun this thing. All right, so I'm going to say, not wanting to overstate, I'd rather under promise and over deliver on my savings. So instead of 19.9% stack loss, if I can run the same temperatures, and of course that's always a question, but you don't really know with any great degree of accuracy what's going to happen to the temperatures. Now, if you've got a big log book and you can go back and forth, perhaps you can adjust temperature. But at this, we're kind of flying at 5,000 feet here. At this cursory evaluation level, you usually assume the temperatures are going to stay the same and we're going to just change the oxygen content. Now, is that perfect? No, absolutely not. But that's kind of the way this game gets played at this level. So if we still had our net stack temperature of 380 and we drop to 3%, that stack loss goes to 18.8. There's another 1.1%. And so then the efficiency is going to go from 80.1 to 81.2. And bingo, I redo the calculation. So now I'm starting at 80.1. I'm going to go to 81.2, and I subtract off that $220,000 in savings that I got from tuning because I already did that. So I've already dropped my operating cost from $13 million to $12,780,000. So I plug those numbers in, and I get $166,000 a year in additional savings if I can drop the flue gas oxygen content from 5 to 3%. Okay. I didn't put a cost. I would say $100,000 would do that project. Not bad. Oh, yeah. Oh, this is a no-brainer. This is another no-brainer. Yep. Okay. Well, okay. So we've kind of went through the O2. Well, you know, what else do we see? Man, I'm putting up you know, and I haven't adjusted my temperatures. I'm still putting up 450. And that's a high stack temperature. If that's out of my last, you know, if that's the temperature I'm actually throwing away, coming out of the last heat exchange surface, that's pretty high. Okay. Well, so when you get into this flue gas temperature evaluation, you got to start looking around before you just jump. Okay. Is the boiler operated at greater than design load? Well, no, because it's 120,000 pounds an hour. If it was 120 and I was making 140,000 pounds an hour steam by overfiring and, you know, just doing whatever, throwing every bit of fuel I could in there to get more steam out of it, then you would expect the temperature to go up and the efficiency to go down. Okay, but that's not the case here. Will the boiler design allow reduced flue gas temperature operation? How many, how much tube surface? What's this thing supposed to do? Go back to the boiler manufacturer. Look in the books when you bought the boiler. You know, at a load like this, what's the flue gas temperature supposed to be? Look in the history books. You know, all this data gets recorded. Go back and look. What was it when it was new? Was it 450 on the first month it operated under these conditions? If it was, I'd say that's pretty much what you bought. Sorry. You're gonna, well, it's not necessarily the end of the story, but I mean, you just didn't buy a lot of heat recovery equipment and tube surface for your boiler. How are your heat transfer surfaces? You know, when you go down for maintenance and open that thing up, get your little borescope and run it. You can go down to Lowe's and buy your little borescope. I mean, it won't be as long as that one, but you run the thing 10 foot down there, you get a pretty good idea what it looks like. You know, is it fouled? You know, is it all sooted up on the outside? You know, what's it look like? When they do the boiler inspections every year, do you have any failed internal components where the flue gases are bypassing the heat transfer surfaces? And is excess air a factor? Because remember, we said if you put too much air in, you will tend to drive the stack temperature up because you drive that radiant temperature down around the fireball and the radiant exchange goes down. So is that a factor? So you got to kind of work through all of that before you start proposing adding additional heat recovery equipment. Because you don't want to tell them to spend $500,000 and then it turns out that, well, the thing was just dirty. You don't get a lot of repeat business doing that. No, you don't. Okay. All right, so here's the deal. Boiler was originally equipped, this is Tennessee Tech. Boiler was originally equipped with a Feedwater Economizer that was taken out of service. The thing wasn't controlled, the flue gases got too cold, we ate holes in the ductwork, and so we told the maintenance guys, chop that son of a gun out of there, we're not gonna do this again. It happens. So there you go. Well, this day and time with all the sophisticated controls, that and the other, maybe we should put this thing back into service. Maybe we should like buy a new one and stick it in there and see what the economics would look like on that. Okay, be repaired, replaced. Okay, so here's the deal. We ought to be able to get down to 300 degrees if we have this Feedwater Economizer. It's probably possible, and that's a very conservative, it's probably possible in a lot of cases to get down 250, 275. So saying 300 is pretty easy with a new economizer. That's not much of a leap of faith. Well, okay, so let's go back to our stack loss table. So we're not sure, you got to figure out what's your base case. We're not sure we can sell the boss on the control system. We don't know. We're going to try. We're going to write it up. But, you know, corporates whining about the amount of money that they got to spend and this, that, and the other. So we don't know if we can get that 100,000 or not. So we're going to go back to the case at the base case right here. 5%. We're pretty sure we can get them to tune it because that's chump change. Okay. 100,000 is not, you know, not the end of the world, but it's still not chump change. Okay. So if we could then go from, say we're starting here, we could reduce it to 300. 300 minus 70 is the net stack temperature, is 230, and that gets that stack loss down to 15.8. Whoa, what is that? Is that 4.1? Yeah, that's 4.1%. That's significant, for sure. So the boiler efficiency could improve from 80.1 to 84.2. There we go. There's our cost numbers. $615K a year. Ooh, I'd like to have a piece of that. Maybe they'll give me a 5% bonus for suggesting it, you know. Estimated $400,000 or $500,000. Still under a 1-year payback. Pretty darn good. So can we save some money on this boiler? Absolutely. Are we going to have to spend some money? Yeah, except for that first tuning. The tuning's almost free. The rest of it's going to be a capital project. We're going to have to spend some money on. Okay, so stack loss reduction. Measure, record, compare. Flue gas exit temperature. What's it doing now? What did it used to do? And other intermediate temperatures as possible. Oxygen content. Is it tuned? And that is a function of boiler load, ambient temperature, and what are our combustibles doing as well. Make sure we can't cut back the air to the point that we don't burn the fuel. We can reduce flue gas exit temperature. Then all of these things could do that. Repair, we have baffles failed, clean the fire side, maintain the water side, install heat recovery components. We've got actually two types of economizer. We've got the standard, which would get us to 250, 300, and then we have the potential for a condensing economizer, which could lower that flue gas temperature down to 100 degrees. But again, you have to have a home. You have to have something cold that you want to heat up. We could preheat combustion air. We don't have an example on that in here, but you can put a heat exchanger in and you can preheat the combustion air before it goes into the burner, and that reduces the amount of fuel that you have to put in. So that 70-degree ambient temperature, let's go back. Let's play with that for a second. Let's go back to measure. Okay, so let's say we're doing this, and let's say we put in we preheat this combustion air, and this goes to say 200. So we're 21%. Well, 17.3 from 21. What's that? 3.7. See, that's possible too. So lots of different possibilities here. Okay. Tune boiler, install automatic combustion control, and challenge. You know, people fall into a habit saying, oh, that's the best we can do. That's the best we can do. A lot of times that's not true. Sometimes it is, but not always. Okay, let's look at resource utilization here for a second. Okay, fuel selection. Sometimes we have flexibility. Fuel selection can provide significant reductions in operating costs due to different different fuels cost different amounts. Sometimes energy cost and maintenance expenditures are offsetting. Example, if you're going to burn a whole lot more green wood or coal, you're probably going to have more maintenance. So you got to take that into consideration. Interruptible fuel pricing can provide great economic benefits. Tennessee Tech is on interruptible electricity, but are we on interruptible? I don't think, I'm not sure. You say for if Tennessee Tech had fuel or had a diesel storage tank and could burn diesel fuel in their biggest boiler, they could go on interruptible natural gas pricing. I'm not sure. I know we do interruptible electricity. I don't believe we do, but a lot of places do, because a lot of these boilers will have what they call dual fuel burners. So the burner can burn natural gas or the burner can burn diesel. Now, you're probably not going to get natural gas in number 6. That's a bit of a stretch, because number 6 is pretty tough to burn. That's a bit of a chore. Number 6 is really cheap, but it's a pain in the rear to handle. You have to keep it 170, 180 degrees to keep it flowing. I mean, a fair number of places that we've been into, natural gas will be their normal fuel, but they've got a big tank of diesel, and given about 30 minutes or an hour, they can change. Sometimes you have to change the orifice out on the burners because the orifice size is different based on, fuel oil or natural gas. Or, it's possible to have a propane tank, because propane is pretty expensive. You wouldn't want to have to burn a lot of propane. But nonetheless, if you have a backup fuel, you can get interruptible pricing, which is, someplace between 10 and 20% savings on your whole gas bill. And they don't call many interruptions. Y'all remember the polar vortex when it came roaring through a number of years ago? It was so cold. Up until the polar vortex, nobody could remember when they had called interruptions in gas and electricity and all that. But the polar vortex was so cold that the electrical system and everybody was sucking natural gas. And so all the interruptible customers got called and said, hey, you got to get off. We're losing pressure in the pipeline because everybody's pulling out so much gas. And so, they have 30 minutes or an hour to make that transition to number 2. And then they get off of natural gas, and then, the demand goes down a little bit and they can maintain the pipeline. So that's a possibility. Environmental issues are huge these days. And you may have a cheaper fuel, but if you can't clean up the emissions effectively, you're probably not gonna be able to use it. And efficiency will change. If I'm burning, say I'm burning number 2, and I get interrupted and I go to green wood, my boiler efficiency is going to plummet from 82, 85%. I'm probably going to be at 70%. Now, if the green wood is free or almost cheap, maybe I don't care. But, the boiler efficiency, you start changing fuels, is going to change some. Okay, so here's a little example. So we've got, what time are we doing? Okay. We got 3 different boilers. Example boiler, let's see. So the green wood does not have an economizer, probably for fouling concerns. So all of them produce steam, are 400 PSIG and 700. The cost of green wood is $2 a million. Cost of natural gas is $10 a million. The cost of number 6, high sulfur, is $5 a million. Now these days, the price of natural gas is probably 3 or 4. But anyway, at least in the example, I mean, natural gas is a great fuel. There's no doubt about it. The boiler capacity is the same. Steam production, so what we're doing right now, we got 80,000 pounds an hour from green wood, 100,000 pounds an hour from natural gas, and 80,000 pounds an hour from number 6. So what is that? 260,000 pounds an hour steam being produced by these 3 boilers. Flue gas exit temperature 400 on the green wood boiler because we don't have an economizer. 300 on the natural gas and 350 on the fuel oil. Oxygen, the flue gas oxygen, we're maintaining 5% across the board. And you see approximate efficiency numbers, 71%, 84, and 87. Okay? So let's investigate further. Okay, fuel selection calculation. So there's economic incentive associated with increasing steam production from the oil boiler. We're going to look at that first, and decreasing steam production from the natural gas boiler. So here's a way that we can calculate these savings. So if you look through here, this nomenclature, capital K is a rate of cost, dollars per year, dollars per hour, whatever. So you got 1 minus 2, so that would be probably the natural gas minus the fuel oil. And tau is time in hours. And so we can substitute for the cap K, the energy rate going into the steam, like BTUs per hour. That's appearing in the steam. The efficiency, divide by the efficiency to get the amount of fuel, and then times the cost of the fuel. And you can do that for the natural gas and the fuel oil times the time. And then we just do a little factoring. So basically, that second equation, if we take the mass flow rate of the steam times the enthalpy of the steam leaving minus enthalpy of the feed water times that bracket term times number of hours, that'll give cost savings per year. Okay? Makes a little more sense when you see the numbers in it. So what we're going to do is we're just going to look at switching 1,000 pounds an hour. Okay? Just make 1,000 pounds an hour less with natural gas and make it with fuel oil. Okay? So there's 1,000 pounds an hour. There's our enthalpy difference, leaving steam minus feed water. And so the natural gas is $10 a million divided by the efficiency of that boiler, 0.842, minus $5 per million, the cost of the fuel oil, divided by the efficiency of that boiler, and then times every hour of the year, 8760. So that's $62,000 a year for every 1,000 pounds that we switch from natural gas to fuel oil. That's kind of interesting. Well, let me see, how much am I making? Well, I'm already making 100,000. Oh no, I'm making 80,000 pounds with my high sulfur oil boiler. So, shoot, I could sure switch 20,000. You know, sometimes it's not a great idea to run a boiler all the way up to 100%. I would not recommend that. If I was doing this for a customer, I would probably recommend 20 or 25,000. You know, because you're not pushing it all the way to the max. Erosion rates, fouling rates, things, you run that thing all the time at 100% load, you're really asking for some trouble, you know. But to take it from 80 to 100, I wouldn't hesitate at that for a minute, or 105, something like that. That'd be pretty easy. If you took 20 off, then you could just switch. The natural gas could go to 80, and the number 6 could go to could go to 100,000. I'm getting tongue-tied, and so that's what, 20,000. So that's 20 times 62,000. What's that? 20 times 62. That's 1.24 million a year just by changing your operating scenario. Whew. That looked good on somebody's bottom line, you know? I mean, not difficult calculations, but sometimes people don't look at this stuff. People don't think about it. Okay. Oh, okay. So we already had a slide. Okay. Modification should be increase. Okay. So, okay. There's that one. All right. So now we're going to say, well, gosh, I got this wood boiler over here. Maybe you ought to do a calculation to generate more from green wood. So let's see what we're going to do. So now we're going to compare shifting from natural gas to green wood. And so we go through the same calculation. The only thing that changes is now I've got, on the green wood, I've got $2 a million BTUs and a boiler efficiency of 0.713. For every 1,000 pounds I switch, I save 91,000 a year. Whoa. Again, you know, you got to worry about maintenance, you got to worry about maintainability, emissions, all those things have to be considered, but that that could be compelling. You know, if natural gas was really this much more expensive, even though, but say, if you leave it to the guys just doing the operations, they're going to burn natural gas because it's so much easier than high sulfur number 6 or green wood. It doesn't make ash. You don't have to clean up. You don't have disposal cost. You have lower emissions. There's lots of things to consider. But if you start running these numbers, you go, hey, come on. Maybe we're not going to go overboard, but we need to start trim back on natural gas and move, you know, expand the use of these other two fuels. Okay, many issues limit fuel switching. I think we've mentioned some of that. Environmental, fuel storage handling, boiler capabilities. How should multi-fuel sites be operated and modeled? Okay, impact cost. The impact fuel is the fuel that will change consumption if steam demands change. So if you were operating, let's say we were going to go fix a bunch of steam traps that were leaking. Okay, so we reduced steam demand by 20,000 pounds an hour. So when you calculate savings, what fuel cost are you going to use? Are you going to average them? Are you going to use the number 6, the natural gas, or the green wood? Well, it goes back to the operation of the plant. What is the plant going to do if steam demand drops by 20,000 pounds an hour? How do they control the boilers? You know, which one is the swing boiler that responds? If you're running 3 boilers, you've got 2 that are probably set and 1 that's responding, moving up and down in terms of changes in steam demand. It's probably the natural gas boiler because it's going to turn up and down better, quicker, react more quickly. I mean, that green wood boiler is not going to turn up and down very quick at all because it's got this big mass of wood in there that's burning. Well, you quit putting much wood in, you still got this big mass that's in there. Natural gas, you're blowing it in. I mean, you cut that valve, bingo, you've reduced the heat input rate immediately. But you know, when you get a big mass of wood, go out on a campfire. Okay, you quit throwing wood in, but you can still sit there by the campfire a long time, right? Because all that stuff is still burning. So it's not going to respond as quickly as a natural gas, and the fuel oil is going to be kind of in between. So when you do the analysis on, say, reducing steam demand, you got to figure which is the impact fuel. That's the one that's going to be reduced based on doing the project. Typically, the highest cost fuel in use is desired to be the impact fuel because then, you know, you reduce a high cost fuel, you get more savings. Blended costs generally do not reflect actual system changes. So you would probably not want to just do some sort of weight averaging on these. Okay, combined heat and power. Steam demands take on many different forms. Reducing steam consumption can often result in most significant energy reduction opportunities. Eliminate inappropriate steam use, reduce appropriate steam use. How are we doing time-wise here? What have I got? I got 10 minutes. Okay, I'm going to haul off here, and I want to take a look at this homework assignment. Because you guys don't have anything to do this weekend. There's no good football on. Okay. Use the measure software to analyze the boiler steam system described below. Briefly write up and analyze the requested projects to improve energy efficiency of the system. Some projects must be done with hand calculations outside the steam system model. This steam system operates 8760 hours per year. Base your calculations on the average condition designed below. So you can assume it just does this all the time. Okay. Come on, silly thing. Okay, so high pressure steam, 400 psi, G, saturated. Okay, so the high pressure steam, the process use at 400 is 20,000 pounds per hour. Medium pressure steam is 180, and its process use is 75,000 pounds an hour. Low pressure steam is 30 psi G, and those are gauge pressures. Is 40,000 pounds an hour. Annual electrical consumption for the entire plant for the whole year is 83,000 megawatt hours, and the average cost of electricity is 7 cents a kilowatt hour. This measure doesn't do demand and stuff separately. That's just 7 cents a kilowatt hour smeared out. Boiler burns natural gas, and the projected future cost that we're going to use is $3.50, 1,000 cubic feet. And each cubic foot is 1,000 BTUs, so 1,000 thousands is a million. So that's per million BTUs. Water cost is $5.50 per thousand. Makeup water temperature is 70. Flue gas analyzer reads stack temperature at 525. Woo, woo, woo. Got some potential there. And the oxygen level is 8.1%. And the CO is 0, which you'd expect with 8.1% oxygen. The average ambient temperature for the combustion air is 85 Fahrenheit. Boiler has positioning controls on the combustion air. Boiler does not have a Feedwater Economizer. Boiler blowdown chloride concentration is gone. Is measured at 3,000 parts per million, and the chloride concentration in the feed water is 210 parts per million. This is for your blowdown calculations. Continuous surface blowdown is the majority of the total blowdown flow. They do some bottom blow, but it's pretty minimal compared to the surface. Use the concentrations to calculate the blowdown percentage of total feed water flow. Your DA operating pressure is 12 psi G. Steam traps. High pressure system, you got 15 traps. MP system, you got 30 traps. LP system, you got 50 traps. Been 5 years since we looked at those steam traps. Studies indicate on average 2% of the steam trap population will fail every year. Assume that a failed trap is blowing live steam into the condensate return system that is at atmospheric pressure. The trap orifice size is 1/4 inch diameter on all traps. So we haven't gotten to the estimate steam leaks, but you can look in the Steam System Survey Guide. There's a little equation in there called Napier's equation. There's also tables available. At this point, there are no turbines on site. That's what we got to talk about next is turbines. We got to get you started. The site has only one boiler with a rated capacity of 250,000 pounds an hour and a rated maximum operating pressure of 600. But we're only operating at 400, but the boiler could operate at 600. Condensate return percentages are reported by plant personnel to be the following. The high pressure steam, 75% of the condensate comes back. Medium pressure, 50%, and low pressure, 65%. Condensate is returned to the atmospheric condensate return tank at 240 degrees. The flash steam is currently vented to atmosphere. So we got a tank out there. We're running all this back into at 240, and it's atmospheric pressure, so it's flashing, and we just let it go. Let it go. The deaerator vent steam is measured to be 2,000 pounds mass an hour. Steam is supplied to the medium and low pressure headers through pressure reducing valves. We're not spraying, we're not doing any de-superheating spray into the PRVs. So you don't have to worry about that. Boiler combustion air fan has an induction motor rated at 125 horsepower. Combustion airflow is regulated with discharge dampers. Measurements taken during the assessment visit on the operating fan motor are voltage AB, voltage AC, voltage BC, current phase A, current phase A, current phase. Oh, that's supposed to be A, B, and C. Oh, sorry. Assume that's IA, IB, IC. I guess a little cut and paste action there, sorry. Steam leaks are minimal and what would be expected of a plant this size. Other than the repair of steam traps, there are no opportunities identified to further reduce steam leaks. So, now some of these things, I want you to go ahead and build the model. Go ahead and get in measure and build the model. It's really, I mean, I've just fed you numbers that are gonna go pretty much, just go in there. You do have to evaluate a stack loss, but you got a calculator to do that. So that's not all that bad. Areas to be investigated in your analysis. Well, reduction of stack loss, i.e. increased boiler efficiency. First, guess what? Assume we can tune it to 5%. That sounds familiar. Next, assume that we're going to put an automatic control system and we're going to take it from 5 to 2% with the stack temperatures remaining constant, costs $100,000. Oh, and this, I've asked you for payback and internal rate of return. If you look in Excel, just Google like in YouTube or something, there's an internal rate of return function in Excel. I'll show it to you, but I'm running out of time today. It's not hard to use, but it's a good tool for you to learn about. So we'll do that. Okay, let's see. And then we're going to put the Feedwater Economizer on C, just like we did. And then on D, we're going to run it all together. We're going to run automatic control system, Feedwater Economizer. So, and that's $500,000 for all projects. 2, reduce blowdown loss via flash steam and thermal energy recovery. So that'll be put in the flash tank and the heat exchanger. Those are just projects you can run. I mean, all you got to do is turn on these projects and bingo, it's simulated for you. So it looks like a lot, but once you get used to doing it, it's not too bad. Cogen, we'll talk more about cogen on Tuesday. I want you to run these various turbines and just use an isentropic efficiency of 55%. The cost of a turbine is $1,500 a kW. So we got some different turbines you can turn on. We'll go over this turbine stuff, like I said, next time. Steam trap maintenance, you can do that as a reduction in steam demand. So you'll have to do some offline calculations and figure out by repairing those traps how much less steam we're going to use. And then you can run a reduction in steam demand. Reduction in flash losses from the condensate receiver tank. You'll have to do a hand calculation on that as well. Add a variable speed drive, variable frequency drive to the combustion air fan. There are calculators online. Rockwell, ABB has a good one, and I will show you that on Tuesday as well. And we want to reduce the DA vent steam to a more typical value. And I would look and see when you first call up the measure program, what does the DA vent rate default to? I think it's 0.5%. I think it's 0.5%. But you'll find that to get 2,000, you'll have to change that vent rate and keep looking at your model. I think it's someplace between, I don't know, someplace around 1 to 2% DA vent rate to get you 2,000 from the model. So anyway, and then, you know, you write me a little report and summarize all that stuff and, you know, summarize it like you would give it to your boss if this was an assignment at work. You want it to be succinct, summary tables, savings, cost, payback. Because bosses don't want to read a 10-page report. They say, hey man, come on, I ain't got time to read this. Give me a page or two. You summarize all of these projects. You know. Okay. All right, so we'll cut it off today, but get in, download Measure, and start trying to build that base model. And then I've got something thrown together. Mine's not complete. And then maybe we can compare some numbers and get you tuned up next time to complete all of this. And I hope you have a great weekend.